Okay, so our examples for chapter or 6.2, section 2 of chapter 6, we're going to keep coming back to this same example of El Dorado Community College. So it starts with a probability distribution. It's a discrete random variable, number of units, or I suppose like credits that students would take, right? So we have this table here. 25% of students take 12 credits, 10% take 13, 5% take 14, and so on. So if we wanted to find the average number of credits, this is what we did in 6.1. We'd put the number of units in L1, probability in L2, and we could do our one variable stats. At least this is how we proceeded to do it. One variable stats, L1, comma, L2. So that would be review, and you can see down here, they're calculating the mean number of credits and the standard deviation, which is what we did in the last section. Okay. Well, now we're going to add a layer to this. We're going to change the variable from number of units to a tuition charge. Okay, so it's $50 per unit. So let's remember these two numbers here, $14 or 14.65 and 2.06. What's going to happen is we're going to multiply all of these numbers up here by 50. So 12 times 50 is 600, 13 times 50 is 650, and so on. You can see the probabilities are the same. What we want to think about now is what's going to happen to that new mean and new standard deviation if we multiply every number in our original list, every variable, by 50. We're multiplying by it. This is what we want to think about. A major concept we want to think about in this section is a linear transformation. So a linear transformation, if you think of a linear equation, y equals a plus bx, generally has two parts to it. A multiplier, right? We multiply the slope times an x value in this linear equation, and then also a y-intercept, which is adding or possibly subtracting a constant. We want to think about what those two things will do to the values of a variable. So the probabilities are still the same. We multiplied everything by 50. Let's take a look and see what happens to the new mean and standard deviation. So you'll notice the new mean is 732.50. And the new standard deviation is 103. So what essentially happened to them? Well, that 103 was the original standard deviation multiplied by 50, and this is the original mean multiplied by 50. So the first part of the linear transformation that we want to pay attention to is how a multiplier will affect the center and the spread. Right? The mean measures center and standard deviation measures spread. And what we notice here in this first example is if we multiply every variable in our distribution by a constant, in this case by 50, then that's also going to multiply the mean by 50, and it's also going to multiply the standard deviation by 50. Okay? So measures of center and measures of spread are both affected by multiplying by a constant. They would just be multiplied by that constant. That's the first big thing that we want to take away from this section. So when it comes to measures of multiplying by a constant, okay? So that's the first big takeaway that we want to think about here. So now we're going to add another piece of this. We're still multiplying by 50, notice, but we're also going to add in this variable t, the tuition charges, right? So it's $100 plus the tuition, right? This variable c. So now let's look what happened. Previously we had this chart over here, right? This was 600, 650, 700. Now look, they've all increased by 100, 700, 750, 800, and so on. So now we want to think about what's going to happen if we add 100 to every number in the list. Okay? What's going to happen to the center and what's going to happen to the spread? And this rule is a little bit different. I want you to consider just this simple list of numbers here. 10, 20, 30. we can see that the center of this list is at 20, right? And the spread is roughly like, they're about 10 apart on average. We could calculate the standard deviation, but we don't really need to, okay? If I multiply all these numbers by 3, let's say, we would have 30, 60, and 90. And that's the transformation that we just talked about. If I multiply everything by 3, the spread has increased too, right? The spread was originally 20, and the spread is now 60, right? 20 times 3 is 60. If we use range as our measure of spread, which is the simplest one we can see. What would happen if I added 5 to all of these numbers? Right? 15, 25, 35. It looks like the center has changed, right? The center had 5 added to it. But how about the spread? 30 minus 10 is 20, but 35 minus 15 is still 20. So it looks like the spread has not changed. So let's see what happens in this example when we add 100 to all the numbers. So recall what the mean and standard deviation were previously. When we multiplied by 50, remember, the mean became 732.50 and the standard deviation was 103. Now when we've added 100 to everything, the mean has been increased by 100 as we'd expect. It went from 732.50 to 832.50. But notice the standard deviation has not changed, right? It's still 103, okay? And the shapes, if we looked at the shapes, they would still, the shape doesn't change from either of those transformations. So that's the second big takeaway. When we add or subtract a constant, it only affects measures of center, not spread, okay? So adding or subtracting a constant to a variable will only affect center, not spread, or shape. None of these will affect shape. The shape of a distribution won't change, okay? So let's see if we can apply that to this next example. In a large introductory statistics class, the distribution of raw scores on a test X follows a normal distribution with a mean of 17.2 and a standard deviation 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So this is going to change all the scores. So we want to know what's going to happen to the mean and standard deviation, okay? So part A, the variable y is going to be those original scores, right? You're going to take x, and he is going to multiply them by 4, and then he's going to add 10 to all of those, okay? So we want to know what would be the mean of y and what would be the standard deviation of y if that were to happen. Well, the mean of y, we're going to start with the 17.2, and we're going to multiply it by 4, right? Both of these transformations will affect the center, right? We'll take 4 times 17.2, and we would add 10 to it, okay? For standard deviation, the adding of the 10 won't change it. Remember the 3 numbers I just showed you. When we add a constant, it doesn't change the spread at all. So the only thing we ought to do to this standard deviation is multiply it by 4. Okay, so I get 78.8 and 15.2. Those would be my new parameters. So now they want to know what's the probability that a randomly selected student has a scaled test score of at least a 90. Well, luckily they told us that it follows a normal distribution, so immediately we can draw our normal curve. And these are our scaled scores. Remember, it's still going to have the same shape. If it was originally normal distributed, it will still have a normal distribution. The difference here is that 78.8 will live in the middle of this instead of 17.2. And now it makes sense to talk about someone who's scoring at least a 90. That's a 90 or above. And this will just be a normal CDF situation for us. We have normal CDF. 90 is the lower limit. Now, standard deviation of 15.2, it's a pretty big number. So if I add 2 standard deviations, that'd be 30.4 to 78.8. I'm already over 100. So let's throw this number up pretty high, like 200. Don't just leave it at 100. That probably won't be big enough. The mean is 78.8, and the standard deviation is 15.2. And using normal CDF, we get a pretty precise answer for that one, 0.2306. So now we're going to come back to El Dorado Community College, and let's think about what's going to happen here now. They have another campus, okay? It's a downtown campus. Downtown has less options. You either take 12 credits, 15 credits, or 18 credits, and that's it, okay? So the mean number of credits down here, we already have calculated here, is going to be 15. That lives in the middle with a standard deviation of 2.3. Very similar to what we did before. What would happen if we randomly select a student from downtown and one full-time student from each campus and combine their number of credits, right? So the first part of this is pretty intuitive. Well, if I randomly select a student from a distribution with a mean of 14.65 and the other student comes from a mean of 15, then on average, their combined distribution will be 29.65. Now, what happens to the standard deviation? Should we just take this 2.3, okay, plus the standard deviation from the previous example, which was 2.06, right? Should we just add those two together, 2.3 and 2.06? Well, let's take a look and see what happens when we do combine these two distributions. So they're doing all the heavy lifting for us here. Don't worry about having to construct a probability table like this. We would not do it this way. This is why I'm going to show you the rule. But what they're doing here is finding the probability that somebody has 24 credits. How would that happen? Well, they'd have to have, or the combined is 12 credits. Well, you'd have to have 12 at the one campus, 12 at the other. So you just multiply those two probabilities, and that's where the 0.075 comes from. So let's not worry about that. Let's focus on what happens here. Where does this 3.1 come from? Well, it's not, it doesn't look like the two standard deviations have been added together, okay? What was added together were the variances. So to get the standard deviation, we would take the square root of the variance, that 9.63. So when we combine two variables, we can add or subtract the centers, but the rule for standard deviation, it's not a direct rule for standard deviation, it's for variance, okay? And the rule is that the variances always add. Okay, and very rarely will you hear me say such and such always. I prefer to kind of think, but this is really true. Whether we're adding the variables or subtracting the variables, we're going to get more variation, and the rule comes back to the variances. So you want to remember that rule, that variances always add, okay? So let's see what happens in this next example. We'll have to work this one out ourselves. So let B be the amount spent on books in the fall semester for a randomly selected full-time student. So suppose that the average amount of books is 153 with a standard deviation of 32. Then they bring us back to these parameters that we had earlier. Recall that the tuition and fees follow a mean of 832.50 with a standard deviation of 103. Okay? Find the mean and standard deviation of the cost of tuition, fees, and books. So what we want to do is combine the average amount of books with the average amount of tuition and fees. So the first part, the mean of the books and tuition and fees, is really simple and intuitive. We would just take 153 plus 832.50. Since I'm adding two variables, it makes perfect sense that I would add those two values. So that part is really intuitive. I think most of you would have been able to answer that first part without me ever even explaining it to you. It just usually makes sense. Now, the standard deviation for tuition and fees. This is not on your formula sheet. You have to commit this to memory. Remember, we're saying that variances always add. So we take the variance for the books, which is 32 squared. We take the variance for the tuition and fees, which is 103. Sorry about that. 103 squared. Okay? And we're going to add them together. Well, that's going to be my combined variance. I want standard deviation, and standard deviation is the square root of the variance. So that would be 107.86. Variances always add. We have to commit that rule to memory. So here we go now. Again, they're giving us our parameters. We don't have to look at those tables or calculate any of these anymore. We have a student from the two campuses, and we're going to take the student from one campus and subtract the student from the downtown campus from that. So again, the mean of this difference should be intuitive. We should expect this to be a negative number. The one campus, on average, a student is going to be paying $732.50, and at the other campus, they're going to be paying $8.25. So if we, and think about it, if we do this many times, if we keep selecting two students and subtract them many times, what will the average difference be? It will be the difference between those two means. Now we'll see who has been listening. Most common mistake I'll see people make here, they haven't studied and pay attention to this, they'll say, well, can't remember what the rule is, but I guess I must just subtract these standard deviations. This is doubly wrong, right? Because on one end, we don't do anything with the standard deviations. And on the other end, the rule is variances always add. We always have to add them. This is why this was the first tattoo I got in college across my back. It says variances always add. This is an extremely important rule. So we take the variance for the first variable, which is 103 squared, and then we take the variance for the second variable, which is 126.50 squared. We add the variances. Well, now we have the combined variance. We want standard deviation, so standard deviation is the square root of variance. Okay, so I get negative 92.50 and $103.61. Let's see if the rest of my examples are still in here. Yep, we have one more. Okay, two more. Suppose that a certain variety of apples have weights that follow a normal distribution. This is probably going to be important if we need to do a probability calculation, with a mean of 9 ounces and a standard deviation of 1.5 ounces. Okay. If bags of apples are filled randomly, selecting 12 apples, what is the probability that the sum of the weights of the apples is less than 100 ounces? So I have to reconcile a couple things. You're asking me the sum of the weights of the apples is less than 100 ounces, but over here my mean is 9 ounces. Well, remember, what distribution are we looking at here? We're looking at the mean weight of the sum of the apples, right? 12 apples. So if on average, one bag of apples, or one apple is 9 ounces, okay, what's the average of 12 apples going to be? 12 times 9, right? So now I'm a little bit closer to having something that makes sense. I know I want the probability that this weight of average weight or sum of the weights of 12 apples is less than 100. But in order to do this, we're going to need a normal CDF situation. Right? This is going to be normal CDF. We can go from 0 to 100 with a mean of 108. And now here's our problem. We need the standard deviation. What is going to be the standard deviation of 12 apples if the standard deviation for one apple is 1.5 ounces? So same rule, the variances add. So what would we do here? We could take 1.5 squared plus 1.5 squared plus 1.5 squared, right? 12 of them, okay? And take the square root of that. Hopefully you can see that this is really just 12 1.5 squares, right? I'm going to have 12 of them, so why not just multiply by 12 and then take the square root? That's my standard deviation for the weights of the 12 apples combined. I added the variances. Variances always add. So now we have our standard deviation, and now we can complete our normal CDF problem and answer the question all the way. So 100 doesn't seem all that far from 108 in the big scheme of things, but it's over a standard deviation down below it, so only about a 6% chance that you get a bag of 12 apples and it's that much underweight, okay, given the mean and standard deviation of each individual, okay? So here we have the speed dating example. Women sit in a circle and men spend about 10 minutes getting to know a woman before moving on to the next one. Suppose the height M of a male follows a normal distribution with a mean of 69.5 and a standard deviation of 4 inches. And the height F of the female speed daters follows a normal distribution with a mean of 65 and a standard deviation of 3. What is the probability that a randomly selected male speed dater is taller than the female? So this always confuses people. What I need here, like how do I determine if one is taller than the other? That's really what they're asking, right? They want to know what's the probability that the male is taller than the female. And this confuses my students because they don't see what the combined variable is, because all they see is that one inequality. So I'm just going to do a simple algebra transformation here and say, wouldn't this be the same as saying the male minus the female is greater than 0? This is the way that we have to think of it so that we know how we ought to combine the two variables. So the distribution that we are interested in is the distribution of male minus female. We could do female minus male, okay, if you wanted to. I just generally think of it, makes more sense to me this way. Female minus male would be less than 0, right? We can do either one of those. But I'm going to go ahead and do male minus female. And the center of that is pretty easy to see. It's going to be 69.5, the average male, minus the average female's height, 4.5. So we're asking the question, what's the probability that he's taller than her? Well, the men are generally taller than the women on average, so we should expect this to be a likely outcome. All right, I'm going to shade all this in. And it's a normal CDF situation again. 0 to, let's go somewhere high, like 10. I might even go higher than that. So like 100, just to make sure, because that standard deviation was 4 inches and 3 inches respectively. So we'll go from 0 to 100 with 4.5 living in the middle. And now we need standard deviation. How do we get the standard deviation? We add the variances. Take the square root. And that's a Pythagorean triple, so I don't even need my calculator for that. Okay. Variances always add. Even though I was subtracting male minus female, the variances still add. Always add them. And we get 0.8159.